Okay, so just to quickly review what we have so far, angular velocity is a vector that's just defined by our change in angle over a change in time. So it has a magnitude and also the direction, which is defined by our right-hand rule, right? We wrap our fingers in the direction of the rotation, and then our thumb gives us the direction of the vector. Multiply that by our moment of inertia or rotational inertia, which is just like our angular rotational mass, I, and we get angular momentum. So that's in the same direction as our angular velocity, using the right-hand rule, just scaled now by the rotational inertia. And then how do we change angular momentum? Well, we do it with torques applied over time, right? The torque applied comes from not just the force and its direction, but also where the force is applied, right? We need a force that is applied some distance away from the axis of rotation and also not completely parallel to the vector that goes from the axis of rotation to where the force is applied. So in other words, there needs to be some amount of perpendicular component between F and its corresponding R. And then, the longer we apply that force or that torque, the more of a change in angular momentum we get. And, of course, the direction of the torque gives you the direction of the change in angular momentum. So just to emphasize the relationships between angular and linear, again, all of this should be, we went over this in detail. The one new piece is kinetic energy. We're not really going to deal with that in this class, but it's good just so you can see the expression is super similar, except we replace m with I and v with omega, so the velocity for the angular velocity. So like in an instance where you have a ball rolling down a slope, we know it's going to have some linear, like some kinetic energy due to the translation, right? We can just, how fast is it moving? And its mass will give us our translational kinetic energy. But then also, if that ball is spinning as it rolls down the hill, which we know it will, there's going to be more kinetic energy due to that rotation that we add to the translational kinetic energy. So for instance, if you had a ball that's rolling down a hill versus a ball that's sliding down a hill at the same speed without rotating, the one that's rolling is going to have just more kinetic energy because that has the translational plus the rotational kinetic energy. So again, we're not going to really do that in this class, but it's good to know and just kind of complete our framework. So this rotational inertia, what is it? Well, it's defined with this expression, and we get it by summing up the contribution to the rotational inertia from each individual mass element. So in easy cases like this, which is the only kind you're going to have to calculate, but you'll just have these discrete point masses with a specified distance away from the axis of rotation, and we just sum up mr squared for each one of those. So this is what's pictured here, kind of at a weird angle, but it's just three masses with like attached by strings maybe, just kind of spinning in a circle around, and so we can add up the moment of inertia of each of them and get the total. We can think of this R. We haven't really seen this much, and we probably won't, again, in a problem, but this R is also really like an R perpendicular. And what I mean by that is, like, let's say you had that scenario with these three masses rotating around. If we displace one of them vertically, so like let's say we just attach one of the strings higher up, so we have something like this, that's not going to change the moment of inertia of that system, right? It's still the same distance away from the axis of rotation. So it's important there that we do have this axis, not just a point. So again, you can either think of this as the distance away from the axis or the R perpendicular away from like a pivot point. If this isn't clear what I'm saying, it's not a huge deal. It probably won't come up. But it is important that there are some changes you could make here that do not affect the moment of inertia. Okay. For solid bodies where it's not just these discrete little points, here's just a bunch of examples of them. Don't bother like writing these down. You'll always be given something like this in a problem or like have to solve for it or something like that, but you'll never have to like use this expression, this integral here. But really it's the same thing before, except now instead of summing up a bunch of discrete individual mass elements and their R squared, each one is infinitesimally small. But this is still really just saying a sum over every little bit of mass over a solid body. Ones to maybe take a specific look at here. On the right-hand side, we have two cases of like a solid body versus one that's just kind of the shell of it. So this here we have a solid sphere and then just a shell, or a solid cylinder versus just a hoop of the same radius. If all of these have the same mass, we can see that the moment of inertia, or rotational inertia, is greater for the shell example or for the hoop than it is for the complete like solid body. The reason being, if we have a solid body that has some moment of inertia, each mass element contributes some mr squared. But if we take that same mass and then just displace all of the mass as far as we can from the center, we're going to increase the r squared of each individual piece. And so we'll get a greater total rotational inertia. So that's why you see, like, I think we did a problem where a hollow bowling ball would have a much higher rotational inertia than a normal solid one. And so you can see the shell, spherical shell, has a higher moment of inertia than the solid sphere, and the hoop has a higher moment of inertia than the solid cylinder. On the left-hand side, these pieces are just emphasizing that if you rotate something about the end point, you're going to get a higher moment of inertia than if you rotate it about the center. Again, just because you're increasing the r of a lot of the mass. Another thing that this kind of emphasizes is the thing I was talking about before, where it's just the perpendicular r that matters, or the distance from the axis of rotation, not just a point. Because, like, let's take a look at this plane right here on the bottom. The plane, or a slab about an edge, the length of it, this b, right, this length does not come into the equation for moment of inertia or rotational inertia at all. Why? Because it doesn't matter how long it just matters how much mass is here. Where along this b axis, or this length we are, does not change how far away from the axis of rotation that we are. So if we took this with the same mass and shrunk it down to a thin rod like above, where it's really dense, or made it really, really long, it would still, as long as it has the same mass, have the same moment of inertia, because that b length doesn't affect it at all. So that's not really something you have to memorize, but it's just good to get an idea for what types of shapes and what type of arrangements of shape and rotational axis give you an increase or a decrease in rotational inertia. Okay, so that's just kind of a review of what we've done so far. These are our building blocks. So now we're going to do a bunch of clicker questions that I think are kind of tough. Some of them tougher than others, but they really get at the conceptual core of this. So first, we have a balanced seesaw. So some arrangement, a plank with a ball hanging on the end, and we're saying in the before picture it's balanced. So it's happy, torques are balanced. Then we take it and we rotate it a little bit with our hands, let it stop, like stop it, and then let go. What's going to happen when we let go? So it's balanced, we take it, rotate it a little bit, and then let go. What's going to happen? So I encourage you to, like, with these, we're not really going to have time to do a ton of work out, but see what your gut says, give a little intuitive thought, and then chat with your neighbor, see what you can come up with. Give you 20 more seconds or so. All right, let's stop there. So the answer is that it will stay tilted. So let's look at why. So first, the before picture, we know it's balanced. So what that tells us is the torques are balanced, right? The torques into the page equal the torques out of the page. The torque on the right-hand side, so that's the one that wants this, from this perspective, to rotate clockwise. So that would be a torque that is into the page, right? And whenever I do these like into the page and out of the page, I really encourage you to do that along with me and make sure that you agree about the direction of torque. Just the right-hand rule takes some practice. So on the right-hand side, we get a torque into the page from gravity on the plank, acting at the center of mass of this plank, right? So that's the nice part about this, like center of gravity is where gravity acts, because we don't need to worry about the piece of the plank that's to the left of the fulcrum. If you wanted to like split this into two pieces and say there's gravity working on this side of the plank and this side at the center of each one, you'd get the same answer as if you just concentrate it at this one point. So I don't know, that's kind of cool. But gravity pulls down on this side, gravity pulls down on the ball on the left side, and they both have some r vector away from the axis of rotation, and so the in torque cancels the out of the page torque. Great. That's true about the before picture. So then let's say we take it and we turn it. What is going to change about what's going on when we turn it? Well, what goes into the calculation of the torques? We have the force and we have the r vector, right? And then the angle between them. Is the magnitude of the force of gravity on these two things going to change? No. The mass of the plank or the mass of the ball isn't changing, and certainly like the mass of the Earth that determines like the force of gravity and the size of the Earth, none of that's changing. So these two force vectors are the same length. Is the angle of the force vector changing at all? Well, I mean, I guess it depends in relation to what, but these force vectors are still pointing straight down, right? Gravity's pulling straight down no matter what, so that doesn't change. The r magnitude doesn't change either, right? The distance from the fulcrum to the end of the plank or the distance from the fulcrum to the middle of the plank does not change, right? Just because we're rotating it. But when you rotate something, the radial distances, by definition, don't change, right? You're just going around a circle. So the length of F, the length of R, and the angle of F stay the same. But we can see here that now the angle between F and R, or the angle of R, however you want to see it, but this theta has changed. Before, the force was perpendicular to the R vectors, right? And so all of the force made a torque. But now when we rotated it, this angle is now less than 90, and so only some of the force is perpendicular to that radial direction. So the torque produced by gravity on each side is going to decrease. The key to answering the question, though, is recognizing that these two angles are the same, right? These two the forces of gravity are parallel to each other, and we're looking at the angle as they intersect the same line. And so, I mean, I guess it takes a little geometry to know that these two angles are going to be the same. But really what we're doing to that torque balancing equation, we had on one side force of gravity on the plank times r equals force of gravity on the ball times that r. And now we've just multiplied both sides by, I guess, cosine theta, but the same cosine theta. So they stay equivalent. The torques actually stay balanced because they both decrease by the same amount. So you could work through that on your own, like writing it out if you want. Yeah? In the case where you have the scale, that's a good question. So the key part is that we tilted it. No, I guess that would still happen with scale, but we tilt it and then let go. I need to think about what's the difference between these two cases. That's a good point. Yeah, let me get back to you on that. Good question, though. All right, let's do another clicker question. We're in a carousel at the center. Maybe we've seen something similar or talked about this. We're at the center of a carousel, and we start walking toward the outside. what is going to happen when that occurs and why. And there's actually I would consider two correct answers to this. So you can answer one, but keep in mind, try to figure out what both of them are. Person was like you're saying after, so like we did the original thing and then a person sat down on it. At that point, then the torque would increase because there'd be a force of gravity on this side, that there was nothing over here to balance.
So how is it just balanced here? Is it because the center of mass is closer to one side?
Yeah, so I mean we're just given its balance, so that just means that like whatever this mass of the ball is perfectly set so that it cancels the force of gravity on this side out. So we just have to take that as like a given. Okay. Yeah. Mm-hmm. All right, let's stop there. So the correct answers for this one are B and D, I would say. So we know the carousel is going to slow down. The most general way to explain that maybe is that there's a set amount of angular momentum that's in the system and no external torque. So that set amount has to stay the same. And so the carousel that has that initial angular momentum shares it with the person. And so if it's shared over more, then it has to decrease. So let's try to do that more precisely, though, with a quick look at an angular momentum chart. So this is, I think, a great example of how these charts can be really helpful. In the initial state, we have some initial angular momentum of the carousel. I'm just going to declare that it's up. This problem wouldn't change if we decided it's the other way, right? Just all of these arrows would be flipped. But if the carousel has an angular momentum that's oriented up, that would mean, like, I guess if we're looking top down, it'd be rotating counterclockwise, but whatever. Just assume it's up, and that's just whatever its rotational inertia is times its angular velocity. We have no initial angular momentum, because we might be like in place rotating, but we have no r vector away from the center. We're sitting right at the center, and so our angular momentum is 0. And so the total initial angular momentum is just whatever the carousel had. Like I said, we have no external torque, so our net change or our total change in angular momentum is 0. And so our final total angular momentum is whatever we started with, the same as our initial, that whatever the carousel had. Then when we walk out, so looking at the delta column, when we walk out, what happens? Well, we gain an r vector. We are now some distance away from the center of the carousel. And so our I, our moment of inertia, or rotational inertia, goes from 0 to whatever this new moment of inertia is, our m times whatever r, depending on how far we walked out. So we gain some angular momentum, right? So now we go from 0 to having some final angular momentum. And if we gain angular momentum and the total change is 0, we know that the carousel has to lose that exact amount that we gained. And that happens because its moment of inertia doesn't change, right? The mass distribution of the carousel itself doesn't change, so we know then that has to come in with the omega, with its angular velocity. As we walk out and gain our own angular velocity, the carousel has to slow down because it gifted us with some of its angular momentum. The other key is that the omega final, our final angular velocity, and the carousels are the same because we are on the carousel. So that's like when two objects collide and stick together, we know they have the same final velocity. Same thing here, if these two objects are attached, they have to have the same final angular momentum. And so we just get that the two final angular momentums are in the same direction as the original, except now the carousel has a little bit less, and we have a little bit more, up from 0. And so I would say that both of these answers are good. The rotational inertia answer, we kind of already decided, right? If we think of us and the carousel as like the whole system with some total rotational inertia, when we walk further out from the center, that rotational inertia increases because our r goes up, and so we have to share the angular momentum over a bigger rotational inertia, and the omega final, the angular velocity, has to go down, where the carousel has to slow down. This equation kind of sums that up. In this bottom row, this is just setting our initial angular momentum equal to our final angular momentum. And so if you just like pull out the omega final, you can clearly see this like comparison of IC times omega c equals IC plus IY times omega final. So like the reason omega final is smaller is because I went from IC to IC plus IY. So that's like the option D explanation. But I would say that we do put a torque on the carousel too. That's also valid. Why? Well, if you look at this middle column, what causes changes in momentum, or angular momentum? Torques applied over time. So because these two columns are they're equal and opposite, but because there's a change in momentum of us in the carousel, that means that we applied equal and opposite torques on each other. Just like when objects collide in space, even though there's no net force, they both exert equal and opposite forces on each other. In other words, whatever momentum gives to one gives to one, then that one gives the equal and opposite amount back. Or, that was a lot of words, but I think you know what I'm saying. So there are torques applied. As we walk out, we do apply a torque on the carousel. And maybe a way to think of that intuitively, like how, if I walk out in a straight line from the center, it seems like the force that I put into walking straight would just be parallel to that r vector, right? I'm just walking out along the radius. So how is that applying a torque, which we need a force to be perpendicular? Well, if you put yourself in that situation, you would see that you actually need to push not just forward, but kind of forward and sideways in order to walk in a straight line, right? I mean, you're giving yourself, as you walk forward, you're going to start spinning with it. And if you didn't, like if you had ice skates on and you tried to do that, you wouldn't be able to stay at the same point on the carousel. So I know it might be hard to visualize, but you do, in fact, when you walk forward, have to put some sort of sideways force that will be perpendicular and be like the normal torque-causing force that we expect. Yeah. Mm-hmm. Exactly. Yeah. So your force, as if you were walking out from the center, your force vector would be like diagonal because you have some pushing you forward and then some preventing you from sliding sideways. Okay. Questions on this one? All right. So the next one is going to be a bit of a spatial brain tease. Not really a brain teaser, but now we're going to start. We're really working in like this 2-dimension, pseudo 3-dimension type thing, but you're going to need to do some more spatial reasoning. So we have a girl standing on a merry-go-round that's spinning out of control, and she wants to stop it by throwing this rock or ball that she has in her hand. So while she's at this position on the carousel that we see here, the angular velocity vector is pointing down, so you need to figure out what that means. But the angular velocity vector is pointing down. What direction does she need to throw the rock or the ball to stop, or at least slow down the carousel? I'm really stumped by your thing about the scale. I'm going to have to like go to my office after this and like figure, I don't know. Yeah, and that's a really great, I mean, if I can't quickly solve it in my head, then it's probably a good question. Okay, let's figure this one out. So the answer, which she did really well on, was out of the page, is where she needs to throw the rock. So let's go through this. First, we figure out that this angular momentum vector pointing down, so we usually do the right-hand rule maybe in the other way, like wrap our fingers and then look at our thumb. But now we take our thumb, point it in the angular momentum vector direction, and we should get this, right? So looking from top down, it would be clockwise. But what that means is the girl at this point is coming out of the page, right? So that's her linear velocity at this point in time, is that she's coming forward, and then we'll go left and then back, but this way. So if we want to stop that, reverse it, well, I guess there's a couple ways you could think of this, but if she's coming forward and she wants to slow down or stop, then she needs to provide a force that is backwards, right? And how does she provide a force on herself that's backwards? Well, we've seen this in collision problems or linear momentum, that she needs to throw the rock, right? If she throws the rock forward, the rock will gain momentum forward, and as a result, she will gain equal and opposite momentum backwards. So that'll be like if she applies a force on the rock forward, the rock will apply a force equal and opposite backward. And so that will slow or stop her motion and the carousel's motion. If we want to think of it more from an angular rotational perspective, we have angular velocity that's pointing down, and so to reverse that, we need to provide a angular impulse or change in angular momentum upward. So we need to provide a force that will provide a torque that is upward. So if we're looking for an upward torque, the force that would provide that at the position of the girl is one that is into the page, right? So same thing, we find that she needs to produce a force at her location that is into the page, and to do that, she needs to throw the rock opposite that out of the page. Yeah. Good question. The torque, or the angular impulse delivered by her throwing the rock, needs to be equal and opposite the total angular momentum that her and the carousel and the rock all have before. So like the force that she throws it with times the r vector, which times the amount of time that it applies for, that angular impulse needs to equal the I, like the rotational inertia of this whole thing, the I omega of what was there before. Right, yeah, so I wouldn't say we're using them interchangeably, because here, up and out of the page, I mean, they're well-defined things. We're just used to seeing this from the top down, in which case we would say the angular momentum would be like into the page, and we could see the rotation differently. So I guess that's really the point of doing this exercise, is to be able to recognize that into and out of the page isn't inherently tied with torque. It's just that that's perpendicular to the directions we're dealing with. So this was just like a challenge problem saying, what if we tilt those axes like this, and now torque applies up and down? But yeah, it's important that when we give answers for like angular momentum and angular velocity, that whatever those are mean rotation or force applied in the direction that's perpendicular, or in the plane that's perpendicular to that direction. So the force from the ball is front and back, but that provides a torque that is in the up and down direction. All right, let's do one more kind of spatial thinking challenge problem. So now we have a helicopter, and it's either in the air and speeding up the direction of the rotors, or it's just starting up, but its rotors are gaining angular momentum in this direction, right? So that would be into the page. And we don't want the cabin, like the body of the helicopter, to spin, right? We want the blades to spin and the helicopter to stay not rotating. So if we want that to occur, what type of force or what direction of force does this tail rotor need to provide in order to allow that to happen? So to give you a little hint with it, if the tail rotor does nothing, then what happens? Well, if we increase the angular momentum of the blades, then we don't have a net torque, right? So the helicopter body has to have an equal and opposite change in angular momentum. So it's going to start spinning the opposite direction, right, if there's no ground or there's nothing to keep it from spinning. So how do we prevent that from happening with the tail rotor? Thirty-ish more seconds. All right, I'm going to stop us there. Okay, so the answer is C, left. Let's figure out why. So first, let's look at the situation where the tail rotor is not doing anything. So in this case, we'll say the helicopter somehow is just no angular momentum initial. So we launch the helicopter from a catapult, and it's just in the air, not spinning, and then we fire up the rotors. But this would be the same thing as if they were already going, and we just increase the speed. We're just going from some smaller angular speed to some larger one. So the main rotor goes from 0 to having some into the page angular momentum. But since we have no net torque, there's no total change in angular momentum. So the angular momentum of the body has to be equal and opposite. And so if the rotors are spinning clockwise, the body is going to start spinning counterclockwise, making it quite difficult to fly. So that's going to be no good. So we need to fix this. So now I'm going to demand that same thing happens to the main rotor, still speeds up in that direction, but I'm going to demand that the body has no change in angular momentum. And the only way to make that true is if we have an external torque, right? Because now the total change is non-zero, and it's whatever change the main rotor's got. So really we just found out that the tail rotor needs to provide this external torque that points into the page. So if we look at where the tail rotor is, we can identify its r vector. It's just this r pointing down from the center to the tail rotor. That's our axis of rotation. And then if we want to provide a torque that is into the page at this point, into the page would mean, again, in this clockwise direction, So we're going to need a force that pushes to the left, which might seem counterintuitive because we found out like the rotors are already going clockwise, right? But then we're going to add another clockwise force. I don't know, it seems kind of weird, but I would just think of it as the angular momentum that we need is in the direction of into the page, right? That's what we need, and this is what gives us that. So really what happens is the helicopter body acts as like a conduit, like it transfers this angular momentum to the blades. It allows the blades to push back against the helicopter. The helicopter wants to rotate, but then it meets the force from this instead. So really where that external force is coming from is from the air. As these blades spin, they collide with tons of air particles. That's creating tons of millions and billions of little collisions with these molecules that provide the force in this direction that keeps it from rotating. So really what's happening is like the tail rotor is allowing the helicopter to push against the air in order to not spin opposite the main rotors. So again, it's a little practice with momentum charts, but really this is just to kind of connect the dots when we have a bunch of different rotating things and have to be very careful about the relationship between the directions of forces and torques. Okay, so this is kind of the end of, well, we might do something later, but what I'm about to do next is going further than we will have to go on an exam or a quiz. Like this type of thinking I think is fair game for next week and for the final, but we're going to go one step further just to analyze some physical situations that I think are interesting and shows the power of this type of thinking. So I'm going to talk about and I'll show you a little video. We're going to try to analyze the precession of a top. So if you're not familiar with this phenomenon, you have these like little spinning tops, and they're spinning around their central axis, but they also start to precess, like in this weird little additional rotation of their rotation axis. And so we can use our angular momentum system that we've built up to describe that. So here I pictured, so now we have a top. It's spinning around this axis, and I want this arrow to point the other way. So I've identified the angular momentum vector as this, which is wrong. We should all see that. If it's spinning, as I've indicated with the blue arrow, that should be angular momentum that points the other way. So you should be able to see that. But forget that. Assume the pink arrow is right. So really it's rotating the other way. It's not super important for this, but it's rotating and it has some angular momentum vector along its rotational axis, which we'd expect. But it's at this angle to the ground, right? Here's where it's in contact with the ground. So let's see what else is going on. We have the force of gravity, right? Gravity is going to act on the center of mass of this top, pointing directly down, right? And now, this gravity is going to provide some torque, not about this central axis, right? Gravity is not going to make the top spin anymore, but about this axis, right? Gravity is going to make the top want to rotate down to the ground, right? That's just like saying if you put something diagonally up, and this is probably going to sound terrible on the audio recording, but if I put something like this, gravity is pulling straight down at the center of mass, and it's going to rotate and fall down along. That's a rotation, if we want to think of it like that. So let's figure out what the torque it applies is. It has this r vector going from the point of contact where it's going to rotate about up to where the force is applied. And so the piece of the force that acts to rotate the top about that axis is this FG perpendicular here, right? The portion of the force of gravity that's perpendicular to the r vector that's going to make it want to rotate downward. So what direction of a torque is that? Well, it wants the top to rotate from this perspective clockwise, right? So that would be a torque that is into the page. So we're going to get a torque due to gravity that is into the page. And so what does a net torque mean? It means that we'll have a change in angular momentum that's into the page. Okay, so now we have an initial angular momentum and a change in angular momentum. And we know how to find the final, right? We just add them. They're vectors. And this is something that's cool about angular momentum, even though we're talking about two different axes of rotation, right? This force of this torque due to gravity is giving us rotation about the axis that's into and out of the page. And this spin that we gave the top is giving us an angular momentum that is along this diagonal in the plane of the page. But just like different components of linear momentum, we can add those together. We can add different components of angular momentum to get a net angular momentum vector. So let's do that. Let's look at it from the top. So this is where, I think it's helpful to do this exercise and cool, but I won't have you do this level of like 3D thinking on your own in a problem. But we look at this from the top down. Now we have our L initial, this L vector that I showed of just the top spinning around its axis here. So from this top-down view, the top is spinning like that. And then the delta L that pointed into the page over here now is just pointing to the left. So do we all see how these two things match up? This top-down view and the left? So then if we just add those vectors, what we find is that our L final is just like our L initial, but rotated a little bit. So this is kind of like when we had a ball going on a string and we were looking at the change in linear momentum that's just always tugged around in a circle. And that's why we get this constant magnitude linear momentum when something is going around in a circle, just constantly turning. We get a similar effect here. The torque due to gravity is constantly wanting the top to rotate downward. But that change in angular momentum added to the angular momentum that it already has makes it, instead of a fall down, be this precession where the axis that rotates around just goes like this instead of actually falling. Just how like when we have a ball swinging around on a string, that inward force from the string doesn't cause the ball to just shoot toward the center. It causes it to continually kind of like fall in, but stays at the same radius. Yeah? Yeah, the final is just L initial, which is that initial spin, plus the delta L that we found from gravity. And so it's just vector addition, like tip to tail, if you add those two. It's hard to combine things in Keynote to add up, but like this triangle should roughly work out. Yeah? The delta L is into the page here, yeah, and to the left up here. Well, it's into the page from this perspective, but here it's to the left. So if we do that, that would be a rotation that is like that way, which means the top is like falling down. But yeah, so let's take a look at what would happen if the top was not spinning, right? So that's another key part. The interesting part isn't just that it ends up precessing around. We found that's kind of cool, but also that when it's spinning, what should happen when the top is off center, just like it falls due to gravity, does not happen. It stays up, right? So what if the top wasn't spinning? If we didn't have that L initial, well, then our L final would just be into the page. And then what happens when we have an L final into the page? That means a rotation that from this perspective is clockwise, and yeah, the top just falls. So the thing that allows the top to stay up is that initial spin. Because when you take that initial spin and combine that angular momentum vector with this change, you get something that is not, well, that is constant in a way. It's constant in magnitude and just changing in direction. So that initial spin is key to keeping it upright. And if you want to go down a rabbit hole with this, you can look up like gyroscopic motion and how gyroscopes work and stuff. But it's all in this same vein, the interaction with angular momentum vectors from things spinning and gravity. Okay, questions on this? This is, again, just a more complex example that should show us the power of these topics and get us to challenge us a little bit. You won't have to reproduce something like this. So another quick thing to mention, I won't go through this in a lot of detail, but hurricanes are a really great little laboratory of angular momentum. Here, the darker red in the center just means it's moving faster, and the purple on the outside means the air is moving slower. You can think of this as a big example of conservation of angular momentum. This is a huge assumption, but if you assume that the angular momentum is constant everywhere, that the angular momentum of the air on the outsides is the same as the angular momentum of the air on the inside, you have some kind of general conservation, then the air in the center, which has a smaller r, right, it's closer to the center, is moving faster, and the air that's further away is moving slower. And that's why they can that proves that they have that similar or equal angular momentum. Here you have larger r, smaller smaller omega, right, smaller angular velocity, but greater moment of inertia because the r vector is large. And on the inside, you have a faster angular velocity, but a smaller moment of inertia because the r is small. So I don't know. You can look up hurricanes. There's a lot of cool stuff. Another, maybe an extension of that, something that occurs, you could look up the Coriolis force or Coriolis effect. It's, again, outside of the bounds of this class, but it is very interesting behavior that you see as a result of conservation of angular momentum and gravity. So you get this, like when hurricanes travel along the Earth, they get deflected by these kind of, I don't know, that gets very complicated quickly, but if you watch like a 15-minute YouTube video on it, you should be able to see a lot of the tools that we've built up just by using the right-hand rule and concepts with conservation of angular momentum. You can really build up pretty complex behavior. It's just kind of difficult to think in 3D like that. Okay, so now something more important that connects all this angular stuff to what we were doing with the linear velocity a bit more. So here's a simple scenario that we have the tools to describe but haven't quite linked up yet. We have a ball traveling in a straight line that hits this plank at the end, and once it does, it sticks. So we know when that happens, it's going to stick, and the plank is going to rotate about its pivot point. So overall, those are two very simple scenarios, right? One where a ball is just traveling in a straight line, where we would probably describe that with linear velocity, very simply, linear momentum. And then the other where we have this rotating system of a plank and a ball, and that would be easier to describe with angular momentum, angular velocity. But to get between them, we don't have a clear way to do that yet. And so to solve a problem where that type of collision happened, we need to build that up. So let's take a step back and look at just a simple case of circular motion. This is a ball just moving with a constant speed, but in a circle. We know the circumference of the circle is 2 pi r, and so the time it takes for the ball to go around once completely is just the change in distance over the velocity, right? Just our delta t is delta x over v. And so we know the time to complete one revolution is just 2 pi r over its speed, right? That's from its linear velocity, or linear speed, sorry. That's how long it's going to take to go in one complete loop. And then we can take that and apply it to our definition of angular velocity, right, which is just our change in angle over our change in time. The change in angle of one full loop is 2 pi, and we just figured out the change in time as a function of our linear velocity or linear speed. And so that simplifies to a very simple v over r. We find that for circular motion, our angular velocity is just equal to our linear velocity over r. Great, and you can see the units work out, right? The units of angular velocity are just per second, or radians per second, but radians aren't really a unit. And here we get meters per second over meters. So again, just inverse seconds. Great. So that's for velocity. Let's move up to angular momentum. So we have our angular velocity. We know angular momentum is just that angular velocity, or angular speed, really, because we're not talking about the direction. But that times its moment of inertia, which for a point mass is just mr squared. Right? So mr squared times v over r, and we get our angular momentum is mvr. And we can go a step further if we want. We know our linear momentum is mv, right? So our angular momentum is really just our linear momentum times r. So now we've built up these neat little relationships between the linear values and the angular values. This is just for this specific case of circular motion, but it turns out we can make that generalization very easily by just saying, by changing this to r perpendicular or p perpendicular. So if the object is not traveling in a perfect circle, maybe some of that velocity is not completely perpendicular to the r. That's fine. We know how to do the trig that gives us the perpendicular component. So what does that mean? Like if we have a ball that's traveling in a straight line, kind of like the example we're trying to figure out, ball that's traveling in a straight line, it has this changing r and changing angle, right? It definitely has some angular velocity. We normally wouldn't think of a ball traveling in a straight line as having angular velocity, but it does, because it's about this axis of rotation. This angle theta is clearly changing. But to calculate our angular momentum, all we care about is not this total r, this distance r, which is clearly getting shorter as the ball approaches, but r perpendicular is not changing at all, right? The perpendicular piece of this triangle, or the piece of r that's perpendicular to the axis of rotation that's going into and out of the board, is this r perpendicular that stays constant. So this ball that's moving in a straight line has a constant angular momentum about this point right here. And so let's take that and apply it to our initial scenario, where we have a ball moving toward this plank that has a pivot point, and they collide and then spin together. So it doesn't have to be circular motion. First, so I guess the question, to phrase it more specifically, is what is the final angular speed of this system? So the ball sticks to it, and it starts spinning. What is that angular speed going to be, given the initial linear speed, right? We have the masses, sure, but all we're given is the v, how fast this ball was moving in a straight line. And we want to turn that into a final angular speed. So first thing to identify maybe is that tau net is 0, right, or F net is 0, but there's no net force or net torque in this system. It's just two objects colliding and interacting. And so our initial angular momentum is equal to our final angular momentum. So our initial angular momentum is just whatever angular momentum the ball traveling in a straight line has. Now we know how to calculate that. It's just mvr. Right here, r is r perpendicular, because this r vector here we're just defining as the length of the plank. Right? So that gives us that constant perpendicular distance from the ball to the pivot. Right? So mvr is the constant angular momentum that the ball has while it's traveling in a straight line toward it. And now that angular momentum has to be equal to the total final angular momentum that the ball and the plank have, because again, there's no external torque. So whatever angular momentum we start with is what we end with. So now let's express the final angular momentum just in terms of what we have here. So it would be the moment of inertia of the ball plus its angular velocity plus the moment of inertia of the plank times its angular velocity or speed. And those two things are the same. Omega f is the same for both because they're stuck together. Right? When the ball hits the plank and they start to rotate around, they're attached, and so the rate at which they go in a circle, their angular speed is the same. And so we can plug in the rotational inertias for each of them. For the ball, it's just mr squared, and for the plank, we're given it's 1/3 mr squared. And now we have an equation. We can set our final angular momentum, this quantity, so mr squared omega f plus 1/3 mr squared omega f, that's just 4/3 mr squared omega f. Set that equal to the mvr, our initial angular momentum for the ball, and we can solve for our final angular speed in terms of the initial angular speed, or initial speed of the ball, right? So we had a situation where we knew something only about the linear component of it, and we're able to relate that to get an answer about the angular behavior. Yeah. Yeah, here I'm just saying r because I've drawn on the diagram that r means the distance from our pivot to the end. But yeah, that r is the r perpendicular for the ball. The r from the pivot to the end. Well, yeah, it's the perpendicular component of the r from the pivot to the ball. The last thing I just want to mention, in the first part we figured out that angular speed is just v over r, right? Omega is v over r. So this is really saying omega final equals 3/4 of the initial angular speed of the ball, which kind of makes sense that it's less because the ball has some initial angular momentum and then shares it with the plank, right? So then the final angular speed that it has should go down a bit because it shares it over a larger moment of inertia, the total of the system. All right, that's all I got for today. Your quiz next week will be on angular momentum and torque. And I'll put out practice quizzes today.